Welcome to our meeting of the tech cluster. Today the meeting is a frontier talk that is organized by the Technological Change and Society Interdisciplinary Research Cluster. The title of today is, as you see, Foundation Models in AI, What Impact for Policies and the Law. Today we are very honored and very happy to have with us Matthias Galle, who has recovered from COVID, and this is the reason why we rescheduled our meeting in April. So Matthias leads several research teams on artificial intelligence at Naver Labs Europe, which is located in France, in Grenoble, if I'm correct. And Naver is a leading Asian technology company. Matthias holds a PhD from the French Institute on Research in Computer Science, on theoretical computer science. And he has worked in industrial research labs on topics on information retrieval, NLP and machine translation. He publishes regularly influential academic papers in top AI journals and conferences. And I think it's particularly interesting in Matthias' curriculum that he also participates in outreach activities and community events like Big Science, that is open source initiative to train multilingual language models. Matthias today will discuss about AI, in particular large neural network, if I understood well, that are typically trained on a large amount of raw data without requiring direct human supervision. And some part of the presentation will be on the new challenges that these models represent for policies like competition law, privacy policy, and for ethical conflicts and issues. So let me just remind you, all of you, the format of our talk. The idea is first to have the presentation of Matthias for let's say from 45, 1 hour, whatever you prefer as a format, Matthias, and then leave quite a bit of time for Q&A and interactions where we will have questions and also trying to answer in both directions. So I also invited Matthias to ask questions to our community. So without further ado, let me really thank you, Matthias, for being with us today, and I hand the floor to you. Thank you.
Thanks a lot, Giacomo. Thanks a lot for being here. This is quite a different experience for me and different audience, but I'm actually very, very excited. I have found, because of my role at my company, I found to be often involved in different types of contracts or collaborations. And there are a number of policy issues which I get asked, which I have no answer to. So I'm very interested in having your ideas on this. I'm also personally concerned about some of the impact of those models for the future society, like any technological change. So I'm very interested in your take on this. One thing I ask you is that if your bandwidth and your background and your shyness allows it, if you could activate your camera, I would greatly appreciate it. My experience of 2 years of teaching and having seminars is that it provides a much more interactive experience if we can see each other's face. Thanks a lot, not necessarily at everybody, but I think if we have 60–70% would be awesome. Thanks. Okay, so yeah, the first I wanted to apologize. I should have given this talk like 4 weeks or something ago, and then well, this happened. I had survived. Sorry, it's a bad name. I had not been sick for COVID for about 2 years, but then I went down last month, and it was pretty tough for 3 days. I'm very grateful I recovered. I'm very grateful for treatments and vaccines which helped me recover. Okay, so the thing's pretty obvious because I guess everybody says this in these kind of talks. I'm not a lawyer, I'm not a policy expert, And as Giacomo said, I actually have more questions than probably answer. This is what I said last time when I was supposed to give this talk, and that is really my attitude here. So I'm trying to give a bit of overview on the technology I'm interested in AI, and then I have tons of questions. I have highlighted a few of those which affect maybe me the most, but I would be very interested in your feedback on any of the points. You should not hesitate to interrupt me during the talk. This is not a problem. It's not like a very structured talk. It's the first time I'm giving this one here, so please do not. I'm not always sure that it's very clear what I'm saying, so please do stop me and ask questions either for clarifications, if you disagree, if you have comments. Please do this. Okay, so what I am, I'm a researcher, an AI researcher. My background is in NLP. My own research is in natural language processing. And I have, ever since my PhD, work in industrial labs. By this I mean corporate research lab of large corporations. This has been for maybe 5-6 years in an American company at Xerox, the photocopy machine company, and then since 5 years now at Naver. Naver, as Giacomo said in the introduction, is a Korean tech company. It is the largest tech company in South Korea. They often call themselves the Google of South Korea. It's one of the few countries where Google is not the dominant search engine, Naver is. And they like to say it's the only country where they don't get help from the government to achieve this. It's much more present, I would say, than Google in the Western world. They are dominant in e-commerce as well. They have the #1 messaging app in Japan, which is called Line, L-I-N-E. And they're becoming a platform for provider for content. So one of the things which is growing quite a bit in Europe is a platform called Webtoons, which is a platform to hold having mangas. Maybe some of your kids, if they are teenagers, have used it. It's a platform where artists can submit their own mangas, which are designed for the phone, and then you can read them as they come out. The role of Naver Labs Europe is to do research for Naver. So we are about 110 people located in Grenoble, as was mentioned. And then I lead, let's say, half of it, about 40 researchers. And I call my group AI for our digital world. So we develop AI techniques for existing or future digital services. And this encompasses stuff like translation, like search, recommendation, something which is called ML Ops, machine learning, which is the operations on how do you operate with machine learning model in production. And we do a bit of multimodal research as well, meaning text plus speech or text plus images. So what I wanted to present today is those 4 points here. I wanted to talk of why the community believes the foundation model is a big deal. I'm going to tell you what those are. I'm going to talk quite a bit about the history on machine learning and trying my argument here is going to be that basically those foundation models is a natural evolution of machine research over the last 70 years. And then I have those consequences for policy and regulations, and it's here where I would have most of my questions, and I guess, and we could start having a conversation. Does it make sense? Any questions so far? Okay, let's go there. I'm starting with this slide here. That's a 2016 match between an algorithm developed by DeepMind, a Google subsidiary, and a Korean champion of Go, Lee Sang-gol. I think normally I have it in my notes, but I can't see them. The reasons I'm highlighting this point here, because it was really like, there are many breakthrough, there are many moments where people said, oh, wait, deep learning is becoming a big thing here. In 2012, there was a competition, academic competition, which is often mentioned, which is called ImageNet. And it was kind of reaching a plateau. And then suddenly there was a submission from a Toronto lab, which basically halved the error rate. And then people said in the image community, oh, wait, it's becoming big. And you could mention 2017, something very similar happened with translation. It didn't really make a big bump in translation at the moment, but there was a very simple algorithm which did as well in German English translation as all the methods were over hyper-tuned until then. And you could probably mention a few years ago with the result of something that's called GPT-3, which is a language model which generates text. So it's a model you type in a prefix and then it generates text as a continuation. Those all were wake-up calls for the community and the society in general, I believe, to say, okay, wait, we are into something big here. I want to talk about this event here because it was really a wake-up call for the Asian world. And working in an Asian company, I get a bit of insights into the whole parallel world which runs there, which we don't see in our daily life in our Western society. But there is right now it really is, it's for sometimes a parallel world in the sense that they're developing research almost in a completely parallel way with their own hardware, with their own software stack. And this event was a wake-up call because Go was considered the pinnacle of intelligence, even more than chess. You probably know this. I am a very bad Go player, but I talked to some Go players who were highly ranked, and they, when I ask them about how they play, they talk a lot about intuition. And I think that's different from chess, where when you talk about chess, people can explain their specific move because they talk about the third or fourth move that they think they will do or their opponent will do. In Go, people often play by intuition. They put a piece somewhere because they feel that this is kind of the right place to put it there. And the fact that an algorithm was able to beat a human expert in a game which seemed to imply some type of intuition was this huge wake-up call in the Asian community. You can see this in the patent applications. You see how this skyrocketed in China in 2016. And this is like, just to give you though everything skyrocketed, right? But I just want to highlight here the huge bump which there was in China. Okay, so neural networks is what brought us here. I'm going to talk a bit more about exactly how they work under Zode a bit. But the continuing growth that you see is fueled by a number of things. One is that we are able to have models which have much more parameters than in the past. It means they have much more flexibility to adapt to a very specific task. This is called the capacity of a model in the learning theory. Something else which brought us here are the use of a special family of functions that are called nonlinear functions. Up to 2012, the most used functions were linear functions, which meant that they were functions where we could find the optimal in a certain way by a certain type of algorithms. With the current class of families, we can't ensure this one. It means that we train our models. We do not know if this is the best weights for this specific model. It's just a very good one. That's what we call a local minimum except of a global minimum. And what is really striking of those things, of the models, is that they are very surprising, the type of output that they provide to an input. So these are two very, very recent examples. Just happens also that both of them are from Google. This is from, the right here is from last week. That's what's called an image generation model. So basically you provide a text input and it generates an image for you. And this is for now a closed model. People can't access this, but you can, if you look on Twitter for this hashtag here, Imagen, which is the name of they gave the model, you can see lots of examples. It's really impressive. What's impressive here is a compositionality that you can find, and meaning that the image was trained with images of a hedgehog, probably with books and forests, etc. But it managed to combine those things, and really the high definition that you can get those things. The other one is another example of a model by Google. It's called the Palm model. And what is impressive here is that this is just one example of many, but what you're basically asking here, this is a model which is trained, it reads text and it outputs text. And so the input here is what is seen here under prompt. And then it basically saying, explain this joke. Of course, the model does not have any grounding of what explain or joke means, right? It just makes pattern matching and just somehow in the training data, it makes a connection between explanation and this output here. And then it makes a joke, which is funny for me because I know what they're talking about, but I think this is funny for like a 0.5% of human population. And the explanation is also, right? When it's explanation, I couldn't give a better explanation. I'd let you read it. I mean, you might find it funny or not, but it really talks about terminology, which is very, very particular. And it makes connection, which I don't think it's all in the training data. So it talks about this piece of technology called the TPU, which is the name of a chip. And it talks about whales, and then about pods, which kind of it's one term which has two different meanings depending if you talk it, if you refer to it in a computing server one or in animals. And I'm pretty sure it didn't see this connection in the training data. So again, it had this compositionality approach where it's able to and sorry for using anthropomorphic language here, but the model managed to take parts of something and to combine them into something bigger. So those things are impressive, right? So you see those things and say, oh wait, something is happening here. I should mention that for the time being, these models, these foundation models, are pretty useless as they are. In the sense that they are striking, it's fun to play with, it's always unexpected what they generate. But they don't solve any specific problem so far, right? So people said that in the future they might disrupt the creative industry. They might provide you a Photoshop, which is much more powerful than everything we have, and why not? Maybe this can happen. But right now, today, it is hard to actually make money with those things. I think in the next few months or years, we will see big corporations being able to make money out of those things by fine-tuning those models into something very specific. So you take this huge monster and then you fine-tune it to solve it one specific task. I believe, and I will come back to this a bit later, that more research is needed to make this available to solve use cases in a broad spectrum. But I believe that when we reach this stage, it will happen at a massive scale. And I will come back to this a bit later.
Matthias, can I ask you one thing?
Please go ahead.
So you said that in your view, what we are seeing here is could not make any money at this stage, right? But of course, it depends on how frequent is the type of this, the quality of this prediction that we see here. But if I think about chatbots, something like this is way better than many of the chatbots we currently see around on commercial websites. So why don't you think that already application of this AI could have some commercial value?
I was maybe a bit too skeptical here. Right now, the results they give are very unexpected. And I think this is something which you don't want if you want to make money. If you want to make money, you want to kind of know what is going to be the results are. You mentioned this, the case of this chatbot. It could be an excellent use case for what's called a companion chatbot. So it's a chit-chat chatbot. It's something where you just want to have an interaction with. And indeed, I started looking into this last year. There is a website which is called AI Dungeons, I believe, which is an interface for role-playing, only text-based, right? So it's a text, it gives you a character, and you start interacting and say, okay, I'm a knight in a medieval image. You enter a village, here's what you see, the system tells you, then you can interact. You can say, okay, I open the door to the bar. What do I see? And it tells you. I spent like, 2 hours playing with this because it was really fascinating, right? The kind of thing that it was a never-ending story which generated there. But it was funny. It was so engaging because it was unexpected, right? So you always had something new. So I believe in this creative aspect. There might be lots of things to be done as it is, right? And now, in order to solve more task-based things like really improving access on bureaucracy when you go to a country, for instance, or really trying to solve translation problem like once for all, meaning like you have the Babelfish, or you have something in your ear and you can just go to a country and speak with. So there is still more work to be done. Mm-hmm. And again, my strong belief is that in a few years, all digital services will be powered by one of those foundation models. So under the hood, there will be one of those. But you need a layer of adaptation to the specific task you want to solve, which is being researched, but it's not yet there.
Right. No, that's quite interesting because you normally think that you normally think that I normally think that these tools are typically very specific, while here what is missing is the specific context.
Excellent. Exactly. So the term that is being thrown around as foundation models, I'm not totally sure. I think I have a slide on this later, but let me say this now. The term which is thrown around as foundation model. This comes from a paper which was published by the University of Stanford last year. Like the whole faculty of computer science published this paper. They created an institute around those things. And the idea of foundation model is not that this is a revolutionary. It's not in the sense of revolutionary. It's in the sense of platform. It's in the sense of it is something on top of which you can build stuff. And people in the community have some issues with the word foundation and the move of Stanford, but the word platform model, I think, explains extremely well what I'm talking about. These are models which have broad set of skills, and you can build lots of stuff on top of this, lots of stuff. It's just that the foundation itself, you can't live in a foundation, right? You need to build a house on top of it. And a house without a foundation doesn't work, but the foundation itself is not really useful.
Thanks a lot.
Okay, so this is my idea. So I hope to to tell you that everybody is very in awe of what happens here. Last week, I was in Dublin in one big natural language processing community conference, and talking to people, I realized that most still think that we have more than scratched the surface, but basically there are lots more of things that we will see over the coming months. And I talked to some of those people which are part of those very large corporations, and they told me things which are not yet public, which are kind of yet being developed. And the overall message is basically there are lots more to come. Like what you have seen public is only just the beginning. And so the community very much believes that this is a big deal. I believe that the society at large is kind of in awe on what is possible. I would like to take a step back now and to talk a bit more about the history and to see how we got here, and trying maybe to make the case that it's not by chance that we got here. That it's kind of it's a natural process on where machine learning has been going, as I said, over the last 70 years. Okay, so let me start with this paper from the 50s, which is a research paper that everybody interested in the field of AI. I very much encourage them to read. It is titled Computing Machinery and Intelligence by Turing. And it's a very pedagogical paper. It's not at all technical. He basically talks about the ill-defined notion of intelligence, and he says, okay, what would it require for a machine to be intelligent? And he looks at the specific case of language, which my own field is natural language processing, so obviously this raises my interest. And people have been doing applications in natural language processing way before the term AI was actually defined. So the term AI, artificial intelligence, is said to have coined in this workshop here, which was a workshop in the 50s. You see some very famous names here: Minsky, McCarthy, Shannon. And they got together for one summer, and they basically said, okay, let's try to crack this problem of intelligence for computers. And well, we are not yet there, but it's basically this proposal, which is the first, as far as I know, reference of the term artificial intelligence. Now, people have been doing translation, for instance, before this, like even 51, 52, there was IBM had published a model, a method, which was doing Russian English translation with the idea of the code word, of course, close by. Though the beginnings of the field generally are referred to in the 50s, right? Because there is this Georgetown experiment, which is this experiment of translation, which IBM did with the University of Georgetown. And then there is this paper by Alan Turing, and then there's this workshop in the US. Those kind of all things that something was brewing in this field. The very first beginnings, like from the 50s up to the 70s, let's say, or 60s maybe, the models which were being used were actually a neural network. And the neural network was of a very simple way. It was only what's called now a one-layer network. And all those are terms. If you've done some very basic linear algebra, you're going to understand it's very easy. The idea is that you have a data point which you want to classify. So you want to say it's either of class 0 or it's of class 1. It's either yes or it's no. And this data point could be a document which you want to know if it's spam or not spam, an image you want to know if it's a cat or it's not a cat. It can be a real estate property. You want to know if it's going to be sold in the next 2 months or not. Whatever, that's the data point. The whole point here is that you don't care about the data point. You care about the variables which define this data point. So this could be the pixel in an image. It could be some metadata of your real estate property, like the square meters, the location, like the price. It could be the different words in if it's a text. So these are basically real value elements. Those are numbers, and you have n numbers, and those n numbers together define your specific data point. Okay, now your intelligence here, your machine intelligence, your neural networks, is going to be the same amount of numbers, like n numbers, which we're going to call weights. Now, the numbers x here, they're given by your data points. The numbers w, they are to be learned by your model. And your model is going to be those numbers and nothing else. And now what you want is that when you have a new data point which comes in, you look at what are the n numbers corresponding to this new data point. And you're going to do the following. You're going to take your weights, which you learned, which your model, and each one of those weights is going to multiply with a corresponding data point. This gives you one number, and you just sum them up, all those numbers. And then you look at the sign of this final number. This is one scalar, it's one final number. You look at the sign of this. If it's positive, you say, okay, this classification is yes. If it's otherwise, so 0 or negative, you say it's not. Okay, so this is a very basic model. It's called the Perceptron. It's a linear classifier. And the way it worked normally is that you had your human designer here, which developed a machine. Now, the interesting part comes that those weights here, it's W, they're not written down by your human, right? They are actually learned out from data, and they're learned out from annotated data. So the assumption is that you have a bunch of data, you have a bunch of point X together with the correct label, yes or no, and you throw this into your machine, and then you get one model out. Okay, so this was quite popular in the 50s and the 60s and the 70s. And that's a model, for instance, which can learn the binary, the logical function AND. Okay, so this is something which people who do chips know a lot, people who do logic know. The idea is that X and Y is true if and only if both X and Y is true, right? So basically this logical statement is true only if the logical value of X is true and Y is true, right? It is sunny and I'm in Barcelona. It's true because I'm currently in Barcelona and it's sunny outside, so both of them are true. But I would say I am in Barcelona and it's rainy, it would be false because one of the two things is false. Okay, logically. Okay, if you want to solve this, you can solve this with, the only thing you have to do is you have to find 3 weights in the past, I only talked about 2 weights. There is a third weight, which is called the bias vector, which is not multiplied by any value. Please just ignore this part. But basically, you need to learn 2 weights, which you multiply by those values, and then you look if it's negative, then it's false. If it's 1, it's true. And there is a set of weights which exists such that it can solve this logical statement. Okay, so basically, this very simple model, this Perceptron, is able to learn the logical function x and y. It's awesome that people are happy. Now there is a problem which was pointed out very, very early on, which is that there's a very simple logical function which is called the exclusive OR function, which is kind of the OR that you and me we use when we talk. It's a one which is true only if exactly one of the predicates is true, but it is not true if both of them are true, right? So it's either you do that or you do the other one. And it so happens that XOR cannot be learned with a linear perceptron. And you can see this very easily in this diagram here. Here to the left, you can see the graphical depiction of the AND statement. So on the X, you have, in the X-axis, you have the value of X, and the Y-axis, you have the values of Y. And then the color here is it's white if the joint X and Y statement is false, and it's black if it's true. Okay, so it's true only if both XY and X2 are true. Okay, and these are 4 points here, and you can see it's very easy to separate those points with a hyperplane. You can draw a line which separates the black dot from the white dot here. And so you can separate it with a hyperplane, so it can be learned with a linear model. The same happens with OR. But the same does not happen with exclusive OR, because you have the description of the exclusive OR here. So it's black only if and only if exactly one of those things is true, right? So this one here is white because both of them are true. So there, you can see there's no hyperplane which separates those two things here. Okay, why am I talking to you about logical statements here? The reason is that people said, okay, look, XOR it can't be solved with a linear perceptron. And it seems like we want to reach the roof of this building here, where we have our general intelligence, and we have a chair here, a ladder here, but the ladder doesn't get us up to here. Right? We can get pretty high, but we can't really jump up to this point here. And this became a bit the end of the early AI revolution. There was a book which was called the Perceptron book, which heavily criticized this and basically said, look, you can't even learn XOR with your very easy learned weights. Ergo, you are not going to be able to learn anything more sophisticated to it. So in the 60s, people basically, people basically dropped this line of research because it was basically assumed that it was not able to learn anything much more complex than easy linear function. Enter then the late 60s, 70s. And there was a new generation of AI methods, which were mostly symbolic systems. And probably the most paradigmatic of this is a person called Chomsky, Noam Chomsky, which is also the guy of my AI designer. It's a comic of Noam Chomsky. I'm hugely indebted to Noam Chomsky personally. My own research is very much inspired by him. He is my ancestor, academically speaking. But he had this idea that you shouldn't develop probabilistic models. You need to design models in the lab, which in his case were grammars, like you can see here. So you design a grammar. So you have an AI designer which knows lots of things, which reads lots of things, and it's the AI designer who develops the machine. But the machine is not per se learned. So the machine does not have access directly to the data in order to learn something. All the data-drivenness comes from the fact that the AI designer interprets this information, draws a rule, and then basically runs it. Those symbolic systems, yes.
Sorry, would you call these the expert systems?
Exactly. So those in the 70s, in the early 80s, were known as expert systems. They're very popular in healthcare, and where you ask doctor to basically sit down and to draw what is their normal chain of thoughts. And this idea was you would encode this in some way, in a system, in a formal way, this system would be able to generalize from there through logical rules, and then would be able to handle new cases. The reasons we don't see those systems a lot these days is because they're not very robust to noise. So this is my favorite example when I talk about noise. This is a US senator, I believe, or I think it's a senator. And that's how he wrote like 7 years ago on Twitter, at the time when you could only have 140 characters. So good luck parsing this with an expert system, right? Because this is so full of noise that you won't have a system which is designed in your lab be able to parse it. And I think language is a perfect example of this, because language is so complex, it's so full of exceptions, it's evolving all the time, and it's full of interruptions, that it's really impossible to have a formal system understanding this. And this is I'm a big fan of this comic strip here, which is called XKCD. And this comic strip basically makes this point that every choice of phrasing and spelling and tone and timing carries countless signals and context and subtext and more. And every listener interprets those signals their own way. Language is not a formal system. Language is a glorious chaos. And expert systems are very bad at handling chaos, right? Because it's so much noise there. So this is the other example I had here, which is that you have words like bank, which have different meanings depending on the context they occur with, and trying to encode the context into formal system is extremely complicated. We work with a translation system. We work a lot on translation. And so in the past, we had developed a translation system specifically for menu translation. There was a big problem when you wanted to translate the word carte in French in the translation, because the most used sense of carte in English is map, but in a restaurant signal you want to have be translated as menu. Okay, so it's the context basically the listener here. It's so important, you need to encode this. So again, we're in this stage here where we had our Chomsky trying to go up with the ladder and reach a kind of good intelligence, like higher level intelligence, whatever, and you realize the methods that you're using are just not good enough. It won't reach the rooftop of the building you want to reach there. So in the 80s, people tried to combine both systems and come in statistical systems. So the idea of the statistical systems were the following. It's kind of a combination of the two things. The idea is that you had an AI designer who knew about his domain or her domain, but the feedback this AI designer provided to the system were not the real rules you wanted the system to use, but were just highlighting which are the signals which are important to the machine to pay attention to. And then you had a machine which was very similar to the previous one, which was a linear model. But the difference was that this X here, which we talked could have been the pixels before, could be the word, or could be some metadata, become now of a much more complex type, and were called features here. And you had lots of time, you had lots of people spending lots of time doing what was called feature engineering. So at this time in the 80s, 90s, you read a paper in computer vision and natural language processing, and you were talking all about a model, and maybe 80% of the paper was about the model, and 20% then were about the specific features that they were using. But then you went and you talked to the authors, and you realized that in reality, the amount of effort they put in is reversed. 80% of their time was spent thinking about what a good feature is. Like, I have this new problem. What is it really, which are the important signals of this model? And you try to extract those, and then you give those signals to a machine, and the machine learns how to weight those different signals in order to make a final decision. So if you do classification of news article, it could be the mention of places, could be certain people, which would mean that you need named entity recognition. You could need the relationship between the different words. So you had higher order features which were coming from your parsing, like, is this verb, is this dependent on this specific noun? And I come back to my example of real estate price. You could think a lot about the location, how do you encode location, about the maintenance cost, about surface, etc., etc. And then you had a whole family of models, which are called the kernel methods, which were in an automatic way combined those features in a nonlinear way in order to create more complex models. So this lasted for a long time, like I said, about 20 years. And those statistical models were the early success of data-driven models. So the first speech recognizer, for instance, were these type of models. The first image recognition, object recognition images were of those types of models. The first translation models were of those types, right? So you extracted the features, you gave those to a statistical model, and then it learned how to combine those features. What happened with deep neural networks is that this idea basically got pushed a bit further. So the idea of a deep neural network was to come back to the original idea of having one layer, of having a linear model of one layer, except that now we had several layers, and that's where the name deep come from. We have several layers of those linear models we have explained in the past. So we had one linear model which does a first transformation of the features. It then passes this to a next layer, which has another one, and so on. Now, if you combine linear layers, the final outcome is only a linear model, because if you multiply linear models, what you obtain is a linear model. So the important part was to add some nonlinearity between each one of those layers. Here we show one of those nonlinearity, which is called the sigmoid function, but you have like dozens of different nonlinearities which people use. This nonlinearity gives it much more expressive power, because now you can express things like the XOR function, which you could not before. XOR, you can't solve it with a linear way, but you can solve it with a nonlinear model. But it also creates something which might not be a problem, which is that you cannot guarantee that you actually obtain the best possible solution, because in a linear, if you do have linear models, you have what's called a convex function, and then you have models which can find the best solution for this specific function. In a nonlinear model, you can't do this kind of things. Now, the advantages those models have is that you don't have to spend time doing feature engineering anymore, because you see in the difference here, right? Here you had the AI expert, he needed to understand really the model in order to tell what the features are. Here you don't really to understand a lot about the model. You give just the raw feature, the raw input to the machine, and the AI designer just designs what type of machine you're looking for. So an example again for natural language processing. In the past, when you did like in the 80s, data-driven statistical model with a linear model, you wanted to do maybe text classification. What you normally did is you had a first step, which is called tokenization. A second one was lemmatization. A third one was called part of speech tagging, which was basically saying, okay, is this specific word, is this a noun, is this a verb, etc. Then you did named entity recognition, which is telling, is this a person, is this a location, etc. And then only you did the classification. Okay, each one of those might have been one linear model, which you were just combining. The promise of neural network is to say, okay, forgot all about this one. We just throw in text, and then the output is the final class. We train this end to end. I don't need all these intermediate high-level features. It's my neural network who's going to learn those things from scratch.
Sorry, Matthias, can I ask you some question?
Go ahead, Fernando.
Yeah, I don't quite understand why this multi-level approach makes it unnecessary to specify the feature. Because after all, you have access all over at all levels. So aren't you still in the need of specifying these features that are operating at each level?
Excellent question. It's really an excellent question. And a lot of the early work, maybe 15 years ago in NLP, a bit less, no, it's not true, sorry, but maybe 10 years ago in NLP, a bit more in computer vision, was about saying, look, I have this neural network, which is excellent on making sense out of raw data, and I have a human expert who knows what to pay attention to, try to combine those things. And there were several attempts which were combining those things. Now, there is a famous researcher, Canadian researcher called Richard Sutton. He published a very, very short article a few years ago, which called The Bitter Lesson. And the point of the bitter lesson is that more expressive model with more data always trumps complex models which require human input. Today, we are at the moment that if you add those additional features by a human, like if you do text classification, you ask a human to, on top of it, add some feature template, it will not hurt the performance, but it will most probably not help it neither. Many times actually it reduces the performance. So we've reached a stage where trying to constrain it even more, the network, by telling it explicitly what are the important signals, is at worst counterproductive, at best a waste of time. Because with enough data and with enough layers, it appears that the intermediate representations that the network learns already capture those things good enough. Naturally, people these days are doing the opposite. They're taking neural networks like this one here, and they're opening up, they're slicing it up, and they're looking, is this layer here good enough, for instance, to understand parsing? The way it works is they add a very small linear classifier on top of here, which tries to learn parsing, another one here, another one here, in order to try to understand at which moment the neural network has enough features in order to solve the parsing problem, for instance. And they actually realize that what happens most of the time, that a neural network like this, at the lower layers, it has enough features to learn syntactic features of text, like part of speech tagging, like to lemmatize a word, etc., etc. And then the higher up you go, it has a harder time learning, like taking one of those layers. It's much harder to learn syntactic tasks, but it's much easier to learn more semantic tasks like parsing, like named entity recognition, like something which requires having a bit more of context in there. Okay, so long answer, the shortest one. You can do this, it doesn't really help.
No, so in some sense, for example, I mean, if you're talking about that NLP type of problems, you are already implicitly restricting the machine to be looking at some sort of language that can be written or can be recorded or can be. But of course, this is just a very small part of the evidence that could be relevant for the problem at hand. Okay, so in fact, you are implicitly really already specifying features that are important. If not, I mean, you could look. I mean, any machine would be, even very powerful machines would be overwhelmed by the amount of data that is generated in the world in every dimension at every second. Okay, so in fact, there is implicitly a very significant feature selection, I would say.
No, you're totally right, and I think we talk about those very, very powerful models of broad skills, but we should probably down sample a bit our enthusiasm here, because when we talk about broad skills, it's about broad skills to solve text problem, or broad skills like, oh, suddenly you can do lots of things with text, and you can do a lot of things with speech, and lots of things with images, lots of things with simulated environment like games. We start to see what we in the community call multi-modal networks. So basically a network which are able both to take as input, for instance, text and speech, and output text or speech. But I totally agree that we are in a very, very early stage right now. And if you would take like the Imagine network I showed, which generates images out of text, you would provide it audio features input, and it would just break down. It wouldn't know what to do. It's a good point.
Yeah, thank you.
One point I wanted to say is why deep neural networks are so popular these days, and not in the 60s when early pioneers were working on those things. The general three reasons that are giving are those three I'm giving here. The third one is maybe less popular, but the first two are very, very known. The first one is compute. You probably you might know the neural networks, what they only do under the hood is they do matrix multiplication. So you do tons and tons of matrix multiplication. It so happens that when they started in 2010, 28, there were already very specific chips developed for hardware computation, and those were for graphics and for video games. NVIDIA was the company deploying chips for your graphic card. So if you had a high-power computer to play some advanced video game, you had a special graphic card, and most of the time it was an NVIDIA chip behind. It's basically a hardware which is optimized for matrix multiplication. The reason is that matrix multiplication has lots of parallel computation because you multiply each one of the rows in parallel. So you perform the same operations on all the rows. And you can see since 2017, which is kind of the race of the growth NLP, deep learning NLP, this is a growth of NVIDIA market capitalization, the 1000%, should have invested all in NVIDIA in 2017. And the reason is it basically grow with the AI revolution, because I very quickly realized, okay, gaming is great, but there is much bigger market over here, and they focused on this one. Okay, so compute is one. We have much bigger compute, and this is what's called the hardware lottery. We have hardware which is being developed for this specific type of models, probably favoring in a way that we don't really realize, right? Because we are tied to the hardware that we have. The second reason is we have lots and lots of data. This is thanks to the digital revolution. This is thanks to social media, where not only experts were providing data, but now suddenly you and me and everybody else was providing data. So the explosion of social media powered lots of the current work. The fact that this data is already in digital form. And then finally, those high-level frameworks that are open source. So you can't see this. So the fact that they are open source, this is kind of an example of give you the number of stars. It's what people do in GitHub. They favorite something. And the fact that those things have been open source, it created a rate of acceleration, which I believe is unparalleled in the past in machine learning, because suddenly everybody could just use the networks that was published by the competitor. Most of the time it didn't really work, but at least you could see it and you can improve it. And you had those high-level frameworks. This is TensorFlow, this is PyTorch, which are the most two popular one. And what they allow you is they allow you to write those networks in a very, very high-level way. Basically, you just say, I want a layer of this form, and I want this nonlinear function, and now just learn. So you don't need to actually code your training, your optimization algorithm by yourself. This is done by something which is called differential programming, which is it computes automatically the way that you would need to train those models based on the architecture that you provide. So you can take a very, very high level, and basically you can operate with software which is of a complexity which is extreme, but which is very well encapsulated and modularized, and it helps you to create new networks in a very fast way. You have tons of PhD students working on those things, which are trying all possible combinations. And then once they hit something, they just publish it and everybody starts using it. So this combination of high-level frameworks, which allow you to iterate very quickly, lots of data to power it, and lots of compute to make the training much faster, is kind of what really is fooling the deep neural network revolution. Okay. One last thing before we talk about the possible consequences, and it's really the main part here. This is just this history so far. I wanted to tell you all of this in order to give you a bit more an idea on how we reached the current stage, which are this use of foundation models. The idea of those large pre-trained models, also known as foundation models, is that, again, like in deep neural network, which we just talked about, you have an AI designer who develops a model which just reads lots of data, and that's it. Now, the difference is that the data it's reading here is not annotated, meaning it doesn't, like in the past, the data you read were Twitter comments together, like movie reviews together with the amount of money they did at box office, a movie, right? And then you had lots of those data because you go to Rotten Tomatoes, you go to whatever movie association, you can combine those things. And now you can very easily train a model which, based on the ratings, tries to predict how much money this movie is going to make. This is called annotated data. So you have the pairs of your data point and the label, and it is exactly this label you're trying to predict. And you have lots of examples of both data points and labels. There is much more data out there which does not have a human label than those which has human label. And the power of those large pre-trained models is what they need is only unsupervised data, which basically is they just read text and they do something. They just look at images and they find patterns there. Once you have those models, you can now fine-tune them to tons of different models for specific use cases. Now, those specific use cases might require annotated data. So what happens these days is that you do translation. You have one big model which is pre-trained just by reading text. So it reads lots of text and it tries to find patterns there. And now it does so in 2 different languages, let's say. And now you want to specialize it to actually do translation. This is a foundation, it's a platform on which you build another application and you provide a few examples of parallel sentences of German English, for instance, and you fine tune this one here in order to solve this specific use case here. Now, in order to do this fine tuning, you need access to this model. You might have heard that the first those models were not released, and even today, the very big models, they are not released. And this is one of the things we are doing with Big Science. We're training one of such large models, and we want to give this out to the research community. So first you need access to those models, and then you need to be able to actually copy it, to fine tune it, and to run this. Those models require sophisticated hardware only to get it run. To give an idea, to run one of those large translation models, you need a server with 4 GPUs. This costs about 100,000 euros. This is what you need just to use this model in order to produce translation. Though not everybody can do this. And that's what I meant when I said at the beginning that I believe that what we're going to see for the next months, maybe a year, is how large corporations are going to use those for solving specific tasks. But the real power of those models is that there are platforms on which lots of other people could build on top of it. But you still need a layer of adaptation, of methods, of tools, which you can give to domain experts, which you can give to my family. We have a small SMEs, which have a baker, which has an e-commerce shop, which are not experts in machine learning, but who maybe would like to, I don't know, they maybe want to run a marketing campaign where people take pictures of their product, and depending on how many people are in those pictures, you get bonus points the next time you buy in this shop, right? So those are campaigns, marketing campaigns, any shop might want to run. Foundation models could be very, very powerful for those type of things. They can't be used for this right now because the shop owner does not have access to this fine-tuning approach. So there is a whole research opportunity here, in my opinion, to create methods and tools which would allow many people to use those things. There are people working on this, and once this happens, we will have lots of other policy issues, because right now we will have lots of people using one model which has been trained maybe by a large corporation or by an initiative like Big Science, but which nobody really understands. And then how do we do these things? We'll come back to this. So the definition of those large pre-trained models is that there are models with lots of capacity. By this, I mean models which have a huge amount of parameters, the W weight I talked before. So instead of having 2 or 3, we're talking of literally billions, like GPT-3 is 175 billions. What we're doing with Big Science have the same 176. The large Palm model, which is this large model which explains the jokes of the whales, had 500 billion of those models, a huge amount of numbers that you need to treat. You need lots of unsupervised data. And then you need a possibility of fine-tuning this for specific tasks. So you need, the idea is that there are broad models because they can solve many tasks at least in one mode very easily. Now, here are a few examples of those things. You might have heard of BERT, you might have heard of OpenAI and GPT-3. This is Dino, which is an image recognition one. This is Wave2Wake, which does audio. This is one which does robot learning. So it learns from different robot movements, and then it can learn very quickly a new task the robot by just watching 1 or 2 examples. So just name and in order it rings a bell in your head. So there is, over the last years, a huge trend towards homogenization. Architecture-wise, so everybody's using deep learning these days. Very few people do use a support vector machine, SVM. A particularity is this one transformer this one architecture, which is called the transformer network, which everybody's using. It's one optimization technique. It's a variation of stochastic gradient descent. It's one optimization goal. It's some type of self-supervised. And all this homogenization is allowing already to learn even broader. And I come back to the question by Fernando on multimodal skills, because you now have, anyway, you have one big architecture, which is learning something for vision and something for text. So it's very easy to combine them in a transformer network, which is even bigger and which tries to learn both of those things at the same time. So in the next month, we will see many more of those multimodal networks coming out, which might be able to solve both image, text, maybe even audio tasks all at the same time.
Sorry, Matthias, can you elaborate what do you mean by self-supervised? Because it seems like a contradiction in terms somehow.
Okay. I skipped this on purpose because I had the impression I was always talking too much about technicalities here, but you asked for it, so let me go over it. And the supervised approach is the one where I take my email and I label it. This is spam. This is not spam. This is spam. This is not spam. And I provide this to a machine of which I expect it to produce exactly the same type of answer, spam or not spam. Unsupervised, in the most strict term, and that's probably what you're alluding is I just look at the data and I try to find patterns inside this data. So a typical case is clustering. So I give you lots of images and I want, like you do e-discovery. You have a legal case, you do e-discovery. You have all these emails of this tobacco industry that somebody is suing, and now you have 2 weeks to go over it. What the first thing you do is you cluster those emails to have all the emails from the CEO, all the emails from the legal department, all the emails which talk about lung cancer in some parts, et cetera, et cetera. And in order to do this clustering, you do this many times in a purely unsupervised way. So there are algorithms who just look at those things and try to group things together which have the similar shape, basically. This is a strict sense of unsupervised. Okay, self-supervised is a weird mix between those things, because what self-supervised does, it doesn't require labeled data, but it frames the problem in a supervised way. A typical example is the following. I take text, which does not have any label, and now I'm going to create a synthetic supervised task, which is going to be the following. The task I'm going to create is I'm going to take any prefix, I'm going to hide everything which comes after this, and I'm going to try to predict the next word given this specific prefix. And now I'm creating a supervised task out of unsupervised data. The supervised task I'm creating is to predict one word out of a prefix, and now I can create lots and lots of data pairs in this synthetic task I'm creating, and I can give this a machine to learn something, to learn the specific task. A different one is for images. I take an image, I, for instance, cut it into 4, and now I'm trying to take any two random squares, cutted images, and I try to predict if they belong to the same original one or not. Or I can take my image and I turn it 90 degrees, and now I take 2 random images and I ask them, is it the same image tilted 90 degrees or is it not? Okay, so those are all ways that I can create synthetically a supervised task out of data which does not have labels. Now, the task I'm solving here is not a task I'm interested in. I'm not interested in solving the problem of giving you 2 images and knowing if one is 90 degrees or the other one. I'm not interested in the task of giving a prefix, what's the next word. Those are not tasks. It's an end user I'm interested in. But the idea is that in the deep neural networks, you just learn these tasks, but you don't really care about the final part, about the prediction. What you care about is about the intermediate representation. And now you take this intermediate representation and you fine tune this for your very specific task that you're doing. So the example we saw on the explanation of the joke, this is a model which was just trained to predict the next word given a context. That's everything it did. This is why it needs a prompt. It needs a prefix to start saying something. Now, it just happens so that if you just say, explain this joke, and you give a joke, it has seen so many examples that it actually managed somehow to explain this joke. But you see, what we're doing now is we are taking a task, which is explain a joke, and we're forcing this into the same format of the synthetic task I forced the network to learn. So this is a definition of self-supervised. Okay, so it's basically, it is unsupervised in the sense that I don't require human labels. It is supervised in the sense that I frame this as a supervised problem. So it's a the supervised signal comes from the same corpus. So there we go, self-supervised. But it's a very good question.
Okay, very good. Thank you. Yeah, but then somehow in this context, I mean, once you have detected the structure, it's implicit that then building on that structure, you are going to really add some genuinely supervised problem that you're later going to be interested in.
Yeah. So right now,
I understand. Yeah.
Right now, the way you need the supervised signal. Again, if you don't, then you have stuff like GPT-3, like this explaining joke, where you can do something, but it's not totally clear. Like you have to force your task into the specific format you're looking for. Now, the amount of data you might need here is teeny, right? You might, with 2 examples, it might be enough, or 3 examples, or 5 examples. Or in translation, maybe hundreds of examples, but it's very, very small compared to the thousands or 10 of thousands we used before, even millions. Okay, a few research tasks. I'm way over my time, but I'm a few of the research challenges which those models have. And those are things people are right now basically working on, right? So one is, and I think this might be the most interesting one, is that how do we operate them in order to allow other people to actually make useful things out of it very quickly, okay? What's the best way of thinking about this? What is the API I need? What is the toolkit I need? What does it mean to do ML ops in the setting? What are test units in the setting? So all of those thinking about how I do software engineering with those models is a huge area of research. There's a whole part about understanding. I'm going to come back about those things. 175 billion parameters. Nobody knows what's going on here, right? And which is a big problem for transparency. It's a huge problem for accountability. I can't give you a stamp of approval of saying this model is never going to say racist things. I just can't. Speed is a big problem, and I'm particularly concerned about speed at inference, which means speed when they run, not so much about training. They might take 3 months to train. I don't really care because normally you do this once. But if I need to wait 10 seconds and if this consumes a GPU, then the cost in energy and in time is huge. Now, I just said I don't really care if it takes me 4 months to train. Right now, the thing that works, and that's the way it works at Naver, I can tell you, is that there is one team which is in charge of updating those models every 6 months, right? Because I wanted to know about COVID, for instance, and the model I trained 2 years ago doesn't know about COVID. I want to know it about whatever recent scandal there was in social media, and about the new person which came out, right? And it's now Ukraine is related to war, whatever. Those are things I wouldn't have known if I would have trained my model 6 months ago. So, but if I need to do this every time, it's very expensive. So how do we incorporate those new information quickly? And then how do we control them in order to have one big model? I give this out, and I might release this in the United States, a generation model, and people might have certain expectations of this type of things it can or cannot say. And now I'm going to release this in an Arab country, and people might have very, very different expectations of what it could or should not say, right? And then I have the same basic model, but I want to somehow constrain it to nudge it towards one direction or the others. And surprisingly, the best way we have right now is to have a filter on top of it. And that's what people do, right? You go to the GPT-3 playground, and what happens is you have a filter there, which basically tries to filter offensive language, whatever this means, right? But it's them who have provided this filter. it is not at all known. There's no standard way of nudging those models to one way or the other. One example which might be more telling here. We at Naver, we're working with robots, and then we train robots to move around with a data-driven model, right? So the model learns to navigate in this environment. Now, you might go to a different place where people have different social expectations of the closeness that a robot should have to a human person, right? Some people might more comfortable with having a robot very close by. Asian culture may be a bit more open with this, other cultures less. How do you add those constraints on top of a pre-trained, learned navigational policies is not known. Okay, so now we open the fun part. So I'm going to talk about three things. And look, I'm just going over the three things. Please don't hesitate to interrupt me. If not, in the end, we just open it up. We can do as you wish. Those are three things I get asked when I work with people. And those are three things I don't have an answer to. And I don't know what the current law says about those things. So reasons why I'm throwing those out. I'm not sure those are the most pressing issues, although I believe they could be. But like in my role, leading 40 researchers, doing collaboration with SMEs, talking to my managers who are not necessarily like corporate executives, those are the questions I get asked. And this is really me, right? So I'm here a cat, and I'm entering a territory I'm not at all familiar with. So please bear with me. All the wrong words, the wrong terms I'm going to use. Please have patience with me. I'm going to be very cautious here. Okay, the first question is copyright IP and what does it mean to fair use here? Probably the most known example is Copilot here. Let me see if I can share. So if I can I do? So Copilot is a network done by OpenAI, which they call it's a pair programming. So basically you give it a prefix. That's what the prefix you gave it. Okay, this text here. And then you hit enter and just generates the rest of code, right? And then if you're lucky, it actually compiles. And if you're very lucky today, it actually solves the problems that you want. So the good thing is you can just kind of give it the documentation. So that's what programmers call the documentation. It basically tells in a human language what you want, and whoop, it generates code that actually does what you're expecting. Okay. So this is a service which is running. A version of it has been deployed in some Microsoft product, and it's called a pair programmer. So people actually are using it already. This was fine. So they started from GPT-3, a language model. They fine-tuned this on lines of code hosted on GitHub, which belongs to Microsoft. And now the big question is, what does it mean for code which somebody wrote, which belongs to the person who actually wrote this code? And now Copilot basically apparently sometimes copy pastes exactly this code, right? So what happens if the code that is generated by this model is exactly the same than the code which is under a very specific license, even if it's on GitHub? And so the software foundation, Free Software Foundation, I believe, has issued a statement on those things. And basically saying, okay, we conclude in both cases, they do not infringe the copyright. But this is their statement. I'm not sure how this works. I understand that fair use is a very American, or at least it's very Anglo-Saxon common law thing. So I'm not sure what this means in Europe. What does it mean? In the future, people will use those things to write novels. So you're writing something, you're what's called a writer's block. You don't know how to advance. So maybe you go to GPT-3 or whatever it's going to be popular at that time. You tell, okay, what would you generate here? And this might unblock you. What happens if this text here was generated by somebody else? What happened if I'm using this to create new music and then it uses a melody which already existed? I don't know. People ask me these questions, right? So the reason why this is a problem is that those large pre-trained models, they are already being used as smart database. Okay, this is a paper which was quite influential, which basically said, look, you can take GPT-3 and you just ask it factual knowledge. This is an opinion paper by people from Google, basically saying this is going to be the future of search. And the way that search normally works is the following: you provided a query. This is your whole collection of documents. A search engine is basically divided into two steps. The first one is that it filters out only the relevant ones, and then it re-ranks the relevant one that's the provided list it gives to you. Now, if all of those things get replaced by a neural network as a database, which is already the case, what happens with the factual statements, the factual text which is stored in this model? Okay, this is a question I have for you. I did read the directive of the copyrighted digital single market. It seems it's a thing. I don't exactly know what it is, but this is a question I have, right? What does this mean? What does it mean in countries who do not have fair use laws? And in particular, what happens? What are the consequences on data which is released under a non-commercial license? And that's a question I get a lot. We develop models which we release under non-commercial license. There is lots of data sets which are out there, which are under non-commercial license. People could use such a model and train this under a data which has been, but nobody will ever know because it's basically a reformatting of those data in a different form. You could see this as a transformation of the data. But it's like if you use an image data set, the transformation is not another images data set. It's a neural network which does stuff with it.
Sorry, Matthias, I have a question. I mean, there is an issue here, but what are the incentives to produce this? Excuse me. What are the incentives to produce this public good? No, in the language of economics. Oh, sorry, I don't know what's happening.
You mean what is the incentive for organizations to actually release it?
Sorry.
Yeah.
No. So what are the incentives to produce these pre-trained algorithms? Let's call them like this, that are going to be in the public domain and then used by other people. Okay, so there's the issue of I mean, it's connected to a copyright, no? So somehow it must be connected to the fact that the developers have the ability to either market them and generate some profit or get some other payoff of some sort that provides the incentives in the first place.
Okay, so I can give you two answers, which I believe I've seen. One is researchers who very much believe in open science and they want this to be out and people to be reused. This is the incentive behind Big Science, which is this one-year initiative, which is started by this French startup called Hugging Face, on which I'm helping co-organize. The initiative is basically, we want to create one of those models. Right now, there is no, last 2 weeks ago, there was one by Facebook, but until then, there was no model of a GPT-3 size, which was out there, which everybody could just download and use. And then the initiative of Big Science was, this is not fair for all the researchers not working at OpenAI or Microsoft. So we're going to produce one of those because research is using those things and we want everybody to use those things. Now, to train those models, it's a multilingual model on 49 languages. And the initiative worked with a number of data providers in different languages who provided data. Not all of this data is publicly available, right? So it was trained on data, which is not necessarily publicly available, but now the model will be somehow, there is a license which is being drawn by some lawyers. The question is there a conflict there? If I train this on data which belongs to somebody, and now somebody's going to use this one, what is the relationship between those things? The other incentive is from corporations to make money, and OpenAI doesn't know how to make money with GPT-3. That's my belief. So they just put it out there. They give access to lots of people in order to find the killer app, like the one application which is going to be used for it. So they want others to make money, and they be the platform basically which provides them to make money. So the incentive of giving access to this through an API here is very much an economic incentive in order to create revenue for the company.
So the word open in OpenAI it's kind of.
Oh, Giacomo, don't get me started. I mean, people have been talking like, yeah, it's like the general feeling that it started with some idea and then it kind of diverted another one.
Right.
But you're totally agree. It's extremely ironic that OpenAI, which is behind many of those advances, like they did big projects which nobody else dared to do in a very fast way, but their models are not openly accessible. One which is very related to this is around the right to be forgotten. And the models, these neural networks, they are extremely good at memorizing data. I mean, they actually, the amount of parameters they have, the capacity is so big that they easily memorize the whole data set on which they were trained on. It's one of the big enigmas, and one of the things that people doing theory in machine learning try to understand is why they're actually able to generalize, because all the theory of statistical learning tells that a network which is over parameterized with respect to the data it sees shouldn't be able to generalize, or so those models can manage to. But so what those people did here, they take one I don't know, GPT-2, maybe one of those language models. No, they trained one from scratch, I believe. And then they prompted it with basically names of people or a social security number of people, like stuff which it has seen very few times. And they realized that all this information is being stored inside those models. There's another complication. This goes into the theory of learning. It's that there is some recent theory which makes the argument that it is impossible to generalize if you do not memorize some cases. So the idea is basically, if you want to generalize the verbs, at least you need to know which are the exceptions. If you want to generalize conjugation of words, you need at least to memorize which are the cases where those do not apply. So good generalization might require memorization. So it might well be that for those networks to actually work in the amazing way that they do right now, they need to learn some of the training data by heart. Now the question is, what happens if things change in the future? Like with public persona, it could be that it learned by heart with the president of Italy and this change, and now you need to change your model. But it could be that it learns by reading news article that somebody did a crime, and then a year later, this person actually acquitted from this crime. And then this person might want to say, okay, I want to erase those other information which is out there. How do you do this with those neural networks? Nobody knows, because updating those neural networks is an open research problem. And I have no idea on the interplay on those articles, for instance, of the GDPR, and the impact on neural networks. Like, I don't know how to erase one fact out of those neural networks right now. I wouldn't know how to take this out of big science. Giovanni, do you have a question? You are on mute.
Mute myself. No, I was wondering, because the idea of the GDPR is that it applies to personal data. So in the neural network, if my name is not a feature, so my name, but then it is a language, so my name is also stored in the network, or it's not stored in the network if the network is generalized. So if my name is not stored in the network, then what the network does is to maybe reconnect. When I input my name, it reconnects my name to the data about me that is in the network. This is what happens.
Okay, so it's a good point. I did not talk about the case, and correct me if I'm hitting the wrong point here. I'm not considering the case where the data was somehow pseudonymized, where I'm removing all the personal information. Now, of course, if I never saw the name Giovanni Sartor, there is no way I could ever say something about it. I doubt that this happened on the trillions of tokens that have been used to train GPT-3. And I doubt that this was done in a way that ensures 100% accuracy. So what I'm basically saying is that one of the another problem of those networks is that they are trained on so much data that no human has seen all of this data, right? So there are some statistical tests which are being done, blah blah blah, but for sure there are going to be some exceptions.
Okay, so sorry. So just a clarification, because usually it is said that while the training set includes personal data, the personal identifiers, these identifiers don't go into the model, and you say it is not true. Also, the identifier go into the model.
Yeah. So maybe a question I have here for you. So this is, for instance, if okay, let's take the case of the Copilot. This is trained on code which is on GitHub, and let's assume, I don't know this, but let's assume it's being trained in an undiscriminate way, like got everything its own. And now assume there is a comment there where somebody put his email address, basically saying, if this code does not work, then please let me know. My email address is here. Let's assume somebody says.
Yeah.
Is it correct to say that, and now assume that this is released on GitHub under a Creative Commons license? Am I allowed to use this data to train a model? This is a question. I don't know.
I don't know. I don't know. The problem is whether there is a legitimate interest, I think, in the context of the GDPR. And then I think that, sorry, I don't want to go too much into that, but if the name is on the training set and is only in the training set and it's not in the model that then is distributed, you may argue that you had a legitimate interest to use this data to train, as long as the model does not include the personal data. This does not mean that you have then that you are entitled to use if the name is embedded in the training in the model, then it will be used in other ways for which there may be no legitimate interest. And this would be the kind of way in which I would frame the issue. But
no, this is I think this helps me already. So what I can ensure you from a technical perspective, that if there is personal information in the training data and the model learned on those training data, I do not know of any method of removing this information out of the network once it was trained.
okay.
You can do hacks, whatever, but I don't know of any sound model which can do this. And so what I would get out is that the only way probably to do compliant probably with GDPR that it should be removed from the training data, so it never saw it.
Okay.
Sorry, Matthias, just to be sure that I understand. So you say that once the model is trained, the only way to get rid of this potentially problematic information is to be sure 100% that gets eliminated is to retrain the entire model.
This is my statement. Yeah. Yes.
Okay.
Yeah. And which, so here's my point. Why I think this was true 10 years ago, right? And with deep learning networks. Why this is a problem now is because of this foundation model, this platform model. Those are models which are trained once, very costly, and now are going to be distributed all over the way. And yeah, everybody's going to use it. And it's not necessarily true that they are going to be retrained from scratch. And especially it's not going to happen if every citizen just raised and says, oh, I want my name to be removed from a training.
Sure. Yeah.
Matthias, can you make sorry, I don't want to profit.
Go ahead, no,
but I think this is very important for me. So assume that your model has the training set includes purchases that people have done on the internet. So there is what Giovanni has purchased, what Giacomo has purchased, and so on. Then on the basis of these records of purchases, a model is built. And then this model is used to predict what other people is going to purchase. So you are arguing that the model does not include only the information that somebody which is a law professor or a professor that works at the UI is going to buy, I don't know, certain kind of oil, virgin oil from Tuscany, but is also including the information that Giovanni is going to do that. Is this true?
Well, it depends. Like, to give an example, we are working with an e-commerce company, which is now known in Italy. I can disclose this public information. It's called Wallapop. Reason why I'm in Barcelona, and we're working with them, and the data that we are seeing is anonymized, so we don't have those names, right? Basically, what I just said, because we never want our models to learn it, because the only way I can guarantee that it's not going to learn anything is if I never told it. Like, you tell a secret, the only way to make sure that nobody tells the secret is not telling you in the first place. What I'm saying is that once it did it, and once it's out, you can't edit it and take it out. You need to retrain it. Okay.
So if the model is built by using the records which include the names of myself and Giacomo, then also the information that particularly Giovanni bought the stuff is included in the model.
It depends exactly which model, and it's not necessarily true. It doesn't necessarily memorize everything. I'm just saying I can't guarantee that it is not in the model. Yes.
Okay, thanks. Sorry for interrupting.
No, that's excellent. It's already knowing what are the big concerns is already helping.
In fact, we are already in the free format part of our discussion.
Let me see, this is the last one. Yeah, okay. So this sits a bit on the ethical and transparency part of it. And again, you will see it's related. I personally would love to see more work on verification of deep learning models. Methods which can make certain guarantees on the output on those models. There is extremely little work on formal verification, especially if you compare what happens normally in the software engineering community. There is quite some work done with documentation. Those are kind of two big proposals. One's called data sheets and the other called model cards. These are the references. And basically what it consists in is to provide detailed information on the training data which was used to train those models. So this is one model card which we did, for instance, on a translation model that we released. And then what we did is that we specify the training data, we specify any pre-processing we did. This is pretty very simple training, a model card, but those things can become as complex as a producer wants them to be. It basically gives you more information on the training data. Now, funnily, those big models which are not openly released say very, very little on the training data. Maybe because they don't want to, or maybe because they can't, basically, again, because just such huge amount of data that you don't even know. So very little work done on formal verification of neural networks, a bit done on documentation of the training data, which comes back to this idea, because the only way right now, once we created those beasts, we don't know how to operate them really. So what we can do is we can control what we feed those beasts in the first place. So there is a bit of work done on controlling the data sets. The problem here, those are, for instance, millions of line pairs, which you can see here. So this is a rather small translation model trained on 360 millions of line. Nobody reads all those things, right? Though it's all done with some automatic filtering. And which I believe, actually, I'm not really sure why I put this slide here. Apologies. And this is basically the number. The number of reasons. The number of times, okay, let's go. The number of AI that has been mentioned in congressional records, and you see this basically includes, this is 2022, so this is why it's not so big. And this is a number of AI-related bills passed in 25 different languages. I believe the reason why there are more and more is because the societal concern is much bigger about those things. I'm not sure that all of those bills actually reflect a reality on the technical ground, but there's obviously lots of concern about those things here. Okay, so I realize those are the points I had. Let me go back to those. many of them are related. So copyright, IP, and fair use, in my point of view, it's very much related to the right to be forgotten. How can I make sure that whatever those models spin out is actually doesn't infringe any copyright or any regulation? And then I can talk more about those problems of explainability and ethics. Very little work done here on the models because maybe the one thing I want to say in explainability. In the past, computer scientists were trained as logicians. So basically, we had axioms, and then we tried to induce things out of those things, and we can prove out of those things. More and more, machine learning is being dominated by people who have more of a physics or a statistical background, where you see a phenomenon, or a biologist, you see a phenomenon, you see an animal, and now you try to study it in the wild, but you don't really try to understand it by recreating it. You just try to study it as a phenomenon which happens in the wild. And this requires a whole different mindset that in the past there were. The people who were doing explainability in the past, there were more the logicians type of things, which they understood all the building blocks and they could now generalize out of them. Now you have something which runs around, and the only thing you can do is you could put it under stress condition and you could see how it behaves in a different environment and then try to conclude things out of it. But the explanations that you get out of those things are not extremely satisfying, like they are as satisfying as explanations that you get from biologists, which can be very good, but they're not really necessarily proofs in a mathematical perspective. And I believe this ties in very much to the work around ethics, where you want to have very clear statement of what you can do. The problem is we can't really give you those statements because we can only give you ad hoc explanations, but we can give you reasons of why those things really happen. I apologize because I took lots of time, and I apologize because I realized I tried to have this as high level as possible. Many times I did deep dive into some of the technical things. I hope I didn't lose too many of you by doing this. I tried to give you at least some of the intuitions and some formula which explains what is behind those deep learning techniques. This is what I had to share. I'm open to continue discussing and answer clarifications, and I would be very curious in having your reaction so far. I understand that some of you already have experience in working with policies for AI models. I would be very interested in having your input on those things. Thanks.
Thanks a lot, Matthias. That was really great and super interesting. So we have slightly less than 20 minutes for open Q&A. So any question from the floor?
Yeah, can I ask a question, Giacomo?
Yeah, sure. So let me just ask those who are interested. So Fernando, then you can go to just raise your hand so I can build a queue of questions. But go ahead, Fernando. We know that you are the first, so go ahead. Okay. Well, so no, it's about what you mentioned a bit in passing as one of the challenges, understanding. And then, I mean, this of course, understanding what you mean by understanding is another issue, okay? But I take that this means having some sort of causality of why things happen the way they happened, and some theory implicit or explicit in it, no? Means many times I've heard, and I sort of agree, that this machine learning really does not really make us, they are undoubtedly very useful and immensely useful, but they really do not increase our understanding. Now, one reason why one might worry about that lack of understanding is that it then really subjects the methods to problems of robustness, no? Since we don't understand why something is happening, why the algorithm is so good at predicting what is predicting, then it's very difficult to know whether it's going to be useful in some other context. In other words, I am a theorist, so to make it very succinctly, my point is, do you think that these methods can be really useful without any resort to theory?
Without any resort to?
To doing theory of some sort, okay? So in a sense, you can describe them as theory-free, and in that sense, particularly fragile in trying to bring them outside of the environment where they have been trained.
I can give you my opinion, Fernando, on this, but I mean, other people might disagree. My opinion on this is that I don't think you can have, no, I think that when people talk about explanation of those automatic decision models, they think about an expert system, a decision tree. The decision tree, the way it works, that it makes a series of sequential decisions. Each one of those decisions is done on top of an aspect which is totally grounded to a reality. So credit scores, okay? Do I give you the credit or not? Okay, what I do is I took at your current salary, I took at whatever real estate you have, I talk about your capacity in the past to reimburse. Like there are a number of different decisions I take. Once each one of those is one step, I end at a leaf, and then at the end I decide if I give you a credit or I don't give you a credit. I believe that's what people would love to have for automatic decision models, because it means that they could actually walk down, they could have said, okay, it is here what I would need to change something in order to have a different outcome, because people might not really want to know if they get the credit, why they didn't get the credit. They might not want to know what they should do in order to get the credit. Now, I believe that providing this type of explanation will decrease the capacity of the model to the power of the model. The typical example is when the taxi driver, when he drives me to some place, before they all used Waze or Google Maps, if I ask them why they took this specific direction, they might be able to give a posteriori decision on why they did this, but it's very hard for them to take the decision on the spot. You ask a football player, a professional football player, why on the field, they took a certain decision, and they will be able to provide you an ad hoc explanation, but it really, it's basically in the moment, it is very hard for a human to give you these type of explanations we are asking machines to give. So I believe that if we really want the explanation, that we are asking of the machines more than we're asking of the humans. And this is my current understanding of my current belief in those things.
But I mean, for example, just to ask the question in another way, there is this important issue in science and also in everyday life, which is associated to the notion of counterfactual, okay? What would happen if I had done something different, okay? So if this I have never tried before, and I have no theory, then no amount of evidence will allow me to answer that question.
Yeah.
You see?
I very much agree. And I believe this hits to the point I mentioned before. I believe what people really want is they want to know what they should do in order to influence the decision. What should be different? What cost is this? I'm not really sure what cost, but what would I need to change in order to have a different? And now people are doing this in an empirical way. Again, like you would do with a rat if you do tests, right? You would put them under stress, you would give them the medicament, and you would see if it actually helps in this specific conditions. And you would raise some different, and you would then make some like you do with vaccines, or you do empirical tests on top of those things. But it's I don't know. I'm not a biologist, but I understand that up to this point, nobody can really totally explain how the COVID virus works. It's an a posteriori decision where people try to do this. But what we can do is we can create different scenarios. We can provide different medicines and see what works, what does not cause side effect, and what does not. So people are taking this empirical approach. Now, it is not at all satisfactory, because it's not based, as you mentioned, on some very solid theory where I can then sit down, it's very robust, and I can know how I tune this and how I modify those things.
Sorry, Matthias, I could not disagree more with you, what you said. Okay. I'm sorry for that. I think, you see, in virus, in COVID, our success is that we understand, well, we, of course, humans, understand so much about the process by which virus mutate, reproduce, spread. That and even at a molecular level, okay, that they have been able to develop vaccines, okay, that by a purely empirical approach would have taken decades to develop, okay? And this is because scientists have an understanding of the mechanism. You see, so this is just an illustration of how different one approach can be to another, okay? That it can be, I mean, really the genuine advancement is in an approach that allows you to do this sort of counterfactuals, okay, in which the present success of vaccines is a very good example.
Okay, it's no excellent counterpoint you did. I would say that I guess in machine learning we're still in the middle ages of medicine, and we're still trying stuff like, what is it? Try bloodletting, because it apparently works. And maybe in hopefully not 300 years, but hopefully in 10 years, we would look back and say, this was really a stupid way of doing things. We now know this would have never worked, or you should never have tried those things. But I see us very, very far away from getting a deep understanding of how those models work. And what I mentioned is that right now this is purely done on an outside. It's treating this as a black machine, as a black box, and then putting this under different conditions to see what comes out.
Very interesting. Sorry to step in. I think Marco has a question. Please, Marco, go ahead.
Thank you, Matthias, for this presentation. It was very interesting from legal perspective. And one thing that caught my attention was in this debate we just had with Giovanni regarding the reach of the right to be forgotten, which also connects with the point you raised on intellectual property, which it all seems to turn out in terms of this empirical question regarding whether you have those things materialized, whether you have those bits of information materialized somehow, whether what you are doing within those large-scale models is something other than memorization, whether you have some mechanism to make sense of that information, then you generate stuff, or whether you're simply aggregating things that are already there somehow. Because if the data you have, if personal data is necessarily part of the model in any meaningful sense, then it might be the case that some solutions might require the kind of remedy that the Federal Trade Commission in the United States has deployed recently. They have had 3 decisions. Instead, they have requested algorithm disgorgement. That is, they made a company simply delete the model they have trained because it had widespread violations of rights. So this is it seems that one way where we need to dialogue, we as lawyers, economists, and computer scientists, is precisely to make sense of how is data represented within those large-scale models, something that might help us as lawyers to make sense of this kind of data. And speaking of this scale, one thing I would like to ask you is about how do you see this growth, the growth in compute as a challenge of make sense? Because one thing that appears here is that people often critique that from a fairness perspective, in the sense that this makes models inaccessible. And then here it would be interesting to hear a bit more of your experience on big science. How does that open? But on the other side, working on big science, do you think it's this tendency of computing, whether it's something sustainable in the long run, whether we can keep throwing compute at problems, or how do you see that going on other than 1 or 2 years or so on?
So what I know from the industry is that we are not done yet creating larger models. There are larger models being trained right now, and there has been some empirical studies on what's called power laws for those models, which basically are telling us how much we can expect if you add more compute or if you add more data to those models. So I would expect even more, even bigger models to come out in the coming 2 years. I believe that research is unfortunately unfair, so this is going to happen. And it's not that corporation will suddenly say, oh, no, we're going to wait now because it's kind of an unfair playing game, and somebody's going to do it. I also think that things catch up very quickly. When BERT, which is a very popular language model, was trained 3 years ago, maybe, it was considered outlandish and that no small university could ever use it. And there's been lots of work on creating equivalent smaller models. Hardware has improved a lot, and right now it can run even on a CPU. So I think both of those phenomena will continue playing, right? Although there will be a few players who are going to push the envelope more. And then with time, there will be a version of those models which can be used by other people. Or, like Big Science is doing, is saying, let's create one of those models first to have it out there so people can analyze it. Because one of the big problems of GPT-3 is that very few people can actually look into those things. And we don't know what are the incentives they have in order to disclose the things that they see or don't see. And so the first idea is just release it. And then there is now a current thinking about, well, once we have it, how can we make it accessible for different people to use it? And which is a different problem, as I mentioned, you do need some computing infrastructure to use it. Maybe one thing I can mention is that a recent evolution in this is that a possible bottleneck going forward is not going to be the compute, meaning we could train bigger models, but it will not necessarily help us. But the compute, the bottleneck, surprisingly as it sounds, might be available data. Though I know of some language models being trained in some languages where they have used all available digital text data in this language. And they've trained a bigger model on the same amount of data, and they're not improving. And the current hypothesis, which has been validated by a very, very recent paper by DeepMind from a few months ago, is that we should train current models with even more data, and we could see an improvement even with the current size of the model. So the current bottleneck might not, or the bottleneck going forward might not be compute creating bigger ones, although people will do this, but the real bottleneck might be amount of data we have, which now enters an interesting problem. If we have already read all possible language, all possible text in one specific language, what other data could be used? And then probably it could be multimodal data in trying to combine them with speech or something like this.
Very interesting.
Thanks.
Other questions?
Hi. Thank you, Matthias. It was a super nice talk. I'm more from the part of NLP, like people, rather than legal part. So no, I was thinking about what you told about the community and how, I mean, we were talking about the how probably regulators can approach these issues, considering like machine learning. But I was wondering about how community, in a certain way, self-regulates it, because I remember I was reading about a case when one model was found super biased. And basically, I mean, what the developers of these models did, they just basically extracted it from the use, right? I mean, maybe you know some other examples of this. And from another point, I was also thinking, you were talking in the beginning of your talk, how commercial use, I mean, how these trained models, okay, they can be used by lay people for commercial uses, right? I mean, when the infrastructure would be ready, right? And how it can aggravate the problem, exacerbate the state of things. I don't know if you can comment on this.
Look, I don't have anything smart to say about the self-regulation. I think it's a problem that's becoming even bigger at large in science, because for decades, science was based on a trust relationship. And we have seen that we are reaching a scale, I mean, every year there are more PhDs than the previous year. We're reaching a scale where this creates problems because we have adversarial players inside the game, right? So we have seen this with reviewing, with predatory journals. Like we're entering a part where just playing with trust might unfortunately not be enough. I know that people in the community have been looking at what physicists did after the Manhattan Project, or what geneticians did a few years ago. There were two important meetings. The name escaped me now, where they basically sat together and said, okay, we're not going to do genetic manipulations on human genes or whatever, right? So it was kind of everybody went together and said, okay, we're not going to do this. Of course, now somebody did, right, a few years ago. So once those things become easier access, you can do those things if you only have like one or two labs in the world, or a few labs who are actually capable of the technology of doing those things. One of the fascinating things of computer science, and one of the reasons why it grows so quickly in machine learning, is because it's very easy to democratize it. It's very, very easy because it's just digital, right? Copying is nothing. It's very easy to do. I mentioned the impact that open source toolkits had here. So I'm not sure that the same framework of what worked in fields which required very, very expensive equipment, how easy this carryovers to a field where you only need an account at AWS in order to run your model. And as you said, one of my concerns is that we are entering a stage now where those models will start to leave the big corporation. There is research done on making them more accessible to many people, because I do believe that the real value lies if many SMEs and users could actually access those. But as you mentioned, this opens up the field, and there will be malevolent players there for sure. Science has also become much more international, which makes it even harder to self-regulate. So the NLP community has since recently an ethics committee where papers submitted to NLP conferences can get flagged, and there is an ethics review committee which go through them. Now, the standard of this committee, which is mostly Western-based, is very different from what might be considered acceptable in an Asian setting. And so I think we are also hitting this issue of the diversity in the field. It's becoming so big that it's not obvious for me that we have a worldwide common understanding of what a correct ethics standard is. I did not answer, Arina, because I don't have a good answer to your question. I mean, you're raising some very good points.
Thank you. Thank you.
Thanks a lot, Matthias. We don't really want to abuse of your time, so we reached the 2 hours. I think it was really excellent, and let me really thank you from the entire community. And yes, thanks a lot. Very useful for us, and of course, feel free to interact with any of us if you want to dig a little bit more some of the topics we have covered today. And yeah, that's all. Thank you.
Thanks a lot for the invitation. I felt honored, and thanks for the interaction. It was lots of fun, and I learned a lot as well. Thanks a lot.